Fluent can solve natural convection problems when both gravity is activated and a temperature-dependent density has been defined. Gravity is activated in the operating conditions panel, as you see here in the upper right-hand corner. After doing this, a body force term will appear in the momentum equation that's aligned with the gravitational vector, which in this example happens to be z. For various reasons, solving the equation exactly as it appears here is not necessarily the most efficient way to solve it. What happens in Fluent is that a modified pressure variable, which we call P prime, is defined, and that's equal to the gauge pressure minus rho naught times G times Z, where rho naught is the operating density. Essentially what this is doing is it's taking the hydrostatic pressure head and the operating pressure out of the pressure field. After you do this, and you collect all of the terms in the momentum equation, it looks like this, where P prime is the static gauge pressure that's used by Fluent for boundary conditions and post-processing. This is important. It means that whenever gravity has been activated in the panel, then all of the boundary conditions that you enter are understood by Fluent to be P prime, and all of the results that you display, such as contours or surface integrals or whatever, are also P prime. The purpose of the pressure transformation that we see here is that it helps to eliminate the effects of round-off error on the calculations, and it also simplifies the setup of pressure boundary conditions, which we'll see in a later slide. Many heat transfer problems include the effects of natural convection, especially for ventilation problems. What happens is, as fluid warms, then some regions become warmer and less dense than others, which causes them to rise through the action of buoyancy. Natural convection can occur in both open domains and closed domains, and this is an example of an open domain natural convection problem. There's an LNG liquefaction site where large amounts of waste heat are dissipated by the air coolers, which you see in the graphic in the rows of blue circles. The direction of the ambient wind is shown in the picture, and the goal of the simulation is to determine whether the hot air clears the site when the wind is blowing in this direction. The picture on the right shows some results. This is an isosurface where the air is more than 5 degrees Celsius above the ambient temperature, and what the results show is that there may be some areas where the hot air doesn't clear the site when the wind is blowing in this direction. It's worthwhile to say a few additional things about the role of reference density in these kinds of natural convection problems. The underlying term for the buoyant force in the momentum equation is the difference between the fluid density and the reference density times the gravity. So rho is the local fluid density, and rho naught is the reference density, which is the operating density that you specify in the operating conditions panel. It's strongly recommended that you set the operating density equal to the ambient density of the environment outside of the computational domain. The reason for this is that the pressure profile at the boundaries is dependent on the value of rho naught, and that's because the value that you enter in the boundary conditions is the modified pressure, P prime, and rho naught is part of that definition. The consequence of this is that if you have a computational domain that has both pressure inlets and outlets that are connected to the same external environment, then when you set rho naught equal to the ambient density, it means that you can specify a pressure of 0 for all of the inlets and outlets, which is very convenient. And on the next slide, we'll see how that works. In this example, we have a natural convection problem with a heated wall, an opening in the roof, and a door. We need to set the boundary conditions for the pressure outlet boundary at the roof and the pressure inlet boundary at the door. If we start by saying that the static pressure at the roof is going to be 0, then that means that the static pressure at the door has to be equal to the ambient density times gravity times the difference in height between the roof and the door, which in this case is h minus y. This means that at the roof, the real static pressure is 0, and the buoyancy component that Fluent's going to use in its modified pressure is rho naught times g times h, where rho naught is the operating density. Similarly at the door, the real static pressure we just discussed before, and the buoyancy component that's going to be used by Fluent is going to be given by rho naught times g times y. We can take these expressions and put them here at the right, and these are the values that we need to enter in the boundary condition panel. It turns out though we can subtract rho naught times g times h from both of these equations, and when we do that, then at the top boundary, the modified pressure that we need to enter in the boundary conditions panel is 0, and you can see clearly as the blue text states that if we set the operating density equal to the ambient density, then this term also becomes 0, and that means that we can specify values of 0 for both the door and for the roof. So this is an important concept for natural convection problems in Fluent with open domains. Typically you very much want to set the operating density equal to the ambient density in the exterior of the domain, because that means that you can set 0 in the boundary conditions panel for all of the pressure boundaries. A cavity is another typical natural convection system. In a cavity there are no pressure boundaries, so in theory you could specify an arbitrary value for the operating density, but in reality a sensible choice for this value can help with convergence. The situation is shown here on the left, where we have a cavity with a hot wall and a cold wall. If we set the reference density so it corresponds to a temperature in the middle of the cavity, then near the hot wall there will be an upwards buoyant force, and near the cold wall there will be a downwards buoyant force. So this encourages the correct flow field from the beginning of the iterations, and the solution should converge easily. On the other hand, if we accidentally set the operating density to a value that's too high, for instance it would be equivalent to maybe a temperature that's colder than the cold wall, then what happens is when you start iterating, you have a very high upwards force at the hot wall, but you also have a high upwards force at the cold wall, even though it's not as high as the force at the hot wall. It's still going in the wrong direction. So if the solution were to be able to converge, it would be the same as the converged solution from the upper case, but it's very likely that the solution would not converge, or it would be very difficult to converge the solution in this case. So the recommendation for cavity problems is to set the reference density, the operating density, to a value that's equivalent to a temperature in the middle of the cavity. In certain kinds of natural convection problems, where density variations in the system are small, we can use a simplification that's known as the Boussinesq model. Normally what happens is the solver has to compute velocity, temperature, and pressure, but with natural convection we introduce one additional variable into the system. Because there's an extra unknown, this means that the computational effort is greater, and it might be harder to converge the solution or take more iterations or things like that. With the Boussinesq model, you go to the materials panel and select Boussinesq as the option for density, and specify a value that's reflective of an average fluid density in the system. It's important not to leave the value as 0 or else the solution will diverge. You also have to define the thermal expansion coefficient beta. You can find values for beta in standard engineering texts, and you probably need to use the slider bar over here to scroll down to the bottom of the panel to enter this value. What happens in Fluent after you do this is that the buoyancy term in the momentum equation, which you see on the left-hand side of the equal sign here, is replaced with an equivalent expression on the right-hand side of the equal sign, where instead of density difference, the buoyancy is proportional to the temperature difference. So this only works when density variations are small. What these variables are, rho naught is the value that you enter for the density under Boussinesq in the materials panel. Beta is the thermal expansion coefficient that you enter here, and T naught is a reference temperature. This temperature should be the temperature that corresponds to the density rho naught. So because of this, the same comments that we saw in the previous slides for setting the operating density rho naught, these also apply for setting the reference temperature T naught. Its value is set in the operating conditions panel, and it's important to choose sensible values for this. Specifically, the value of T naught should be the temperature at which the fluid has a density equal to rho naught. On this slide we have a few useful tips and tricks for natural convection problems. As we've already seen, the operating density is very important in natural convection. For problems with cavities, this value should correspond to an average density in the center of the cavity, or if you're using the Boussinesq model, you should set the reference temperature in the operating conditions panel to the median temperature in the center of the cavity. For problems with natural convection in open domains, the operating density should be set to be equal to the ambient density. Only the Presto or body force weighted pressure discretization schemes can be used in natural convection problems. If you choose any of the other pressure discretization schemes, it can result in non-physical flow behavior near the wall. For turbulent flows, it's generally accepted that the first grid point should be at y plus equals 1 in order to get accurate results. But you do have to remember this is not a magic number, and you also need to have several inflation layers with a growth ratio that's no greater than about 1.2. For flows where the Rayleigh number is high, you can use the pseudo-transient solver and estimate the time step using the expression here, where L is a typical spatial dimension in the domain, maybe the height of the cavity, and delta T is a representative of the difference between the high and low temperatures in the system. And finally, for buoyant stratified flows, it's recommended to use one of the K epsilon family of turbulence models.